Hey, welcome back to AP Chemistry with Mrs. Mays. Today we're going to work on stoichiometry. You ready for this? We're going to hit limiting reagents. So hold on, get your calculator out and let's get started. Stoichiometry helps us interpret the meaning of a balanced equation. Remember, balanced equations can be used to describe reactions in terms of atoms or molecules, and in terms of moles, which would mean billions of atoms, right? 6.0 times 10 to the 23 atoms. So either way that you're looking at it, a balanced equation is describing particles, but it's not describing either mass or volume. Now we can get to mass and volume, but as it's written, it's describing individual particles or moles of particles. Chemical reactions happen when molecules collide. So it happens with just a few molecules at a time, but because there's so many molecules in there, then we see an overall large-scale reaction. So it could be a few molecules, or it could be many billions of molecules reacting at a time. Or it could just be, in a very dilute solution, maybe just dozens of molecules, or pairs of molecules, right? However it works, a balanced equation gives us that perspective. The limiting reagent is going to be the reactant that runs out first. It's the one that determines the amount of products that can be formed. Like I said, it's the one we run out of first. And once it's gone, then we can't make any more product. That's why it's called the limiting reagent. To determine the limiting reagent, you have to do at least 2 stoichiometry problems. You'll figure out how much product can be made by each reactant and compare the two amounts and see which one is the smallest. The one that makes the least is going to be considered the limiting reagent. Let's try an example so you can see how this works. Ammonia is produced by the Born-Haber process, where nitrogen and hydrogen are combined to form ammonia. The question says what mass of ammonia can be produced from a mixture of 100 grams of nitrogen and 500 grams of hydrogen. So here's my target, mass of ammonia, and I'm going to do one t-table with 100 grams of nitrogen. The other one starts with 500 grams of hydrogen. So we'll start the first one with grams of nitrogen. What's your first step in almost any problem? Right, we're going to go to moles then. Go to moles. So 1 mole of nitrogen weighs how much? Remember, there's 2 atoms of nitrogen in every molecule. So instead of 14 grams per mole, it's going to be 28 grams per mole because there's 2 atoms of nitrogen. Now we'll use our balanced equation to put in our mole ratio. Oh, I didn't even balance this yet. Let's see, this one, I need a 2 here, a 3 here, and then we're good. Okay, now I can continue with the problem. So 1 mole of nitrogen goes on the bottom because I use crisscross to cancel out my units. And then I want to get to ammonia. So we'll put 2 moles of ammonia up top. But that's not the question. The question asked for grams of ammonia, so we still have to change grams to moles, or moles to grams, that is. So 1 mole of ammonia, add up 1 nitrogen and 3 hydrogens, is 17 grams. Okay. Now get your calculator and work this math through. Okay, so we had 100, We had 100 grams of nitrogen times 2, we'll multiply across the top first, and times 17 grams per mole. And then we need to divide that amount by 28 grams per mole for nitrogen. And, oh, that's all. Okay, so that gives us 121.42. And that was grams of ammonia. So we have an answer, but we're not sure if it's the right answer yet or not, because what if we run out of hydrogen first? Then we wouldn't ever make that much. So let's try the other t-table, starting with 500 grams of hydrogen gas. So now let's check the hydrogen and see how many grams of ammonia we can get out of 500 grams of hydrogen. 1 mole of hydrogen is made up of, 2 atoms per molecule, so that's 2 0.02 grams per mole, right? We could just call it 2 grams. No need to go crazy here. Then what? Use your balanced equation. Hydrogen's on top, so it's going on the bottom next. For every 3 moles of hydrogen, we have only 2 moles of ammonia being produced. And then every mole of ammonia weighs 17 grams. So it's calculator time again. Let's work this one through. So we start with 500 grams and multiply across the top. Times 2 times 17. Get your calculator and check my work, because every once in a while I do make a mistake. And I want parentheses around my denominator. There we go. Wow, that's a lot. 2,833. I think it's pretty clear to see which one is our limiting reagent, isn't it? We're never going to get 2,833 grams of ammonia. That's not going to happen, because look, our nitrogen ran out way back here at 142 grams. So we know that nitrogen is the limiting reagent. So I'm going to identify that right here. Nitrogen is the limiting reagent. We can only make 121 grams of ammonia, and I get to keep, because the decimal's in the back here, I get to keep 3 sig figs, so that can go away. But I'm not done yet. There's a follow-up question. There's always a follow-up question. All right, the follow-up says, how much unreacted material remains? So we take our limiting reagent, and we start every other follow-up question with the limiting reagent. Nitrogen ran out first. So let's see how much hydrogen got used up in this reaction. So for every 28 grams, I get 1 mole of nitrogen. And in my balanced equation, I show that it takes 1 mole of nitrogen to react with 3 moles of hydrogen. Right? And now let's change moles to grams, and we're almost there. For every 1 mole of hydrogen, it takes 2 grams. Calculator time again. Here we go. Multiply the top times the top. I did not need a calculator for that math. Then we divide by what's on the bottom, and I did not need parentheses there. Okay, so it looks like we're only using up 21.4285, whatever that is. So we used up 21.43 grams of hydrogen, and I started with 500 grams. So 500 minus 21 gives us how much? 479 grams of hydrogen remains. So we have way more hydrogen than we ever needed to use. So now you know how to use the limiting reagent in a problem, but it takes experience to get good at this. And don't worry, I'm going to give you a chance to gain lots of experience. Let's look at that excess reagent. The excess is the reactant that you do not run out of. The amount of stuff that you make is the product. The excess reagent is going to be left over. And the product helps us to determine the percent yield. You see, the theoretical yield is the amount you would make if everything went perfectly fine in your experiment. So how many of you have done an experiment and everything goes exactly the way you want it to go? Yeah, me neither. It doesn't do that. So the experimental yield, or we call this the actual yield, is what you make in the lab. Some people call this your experimental yield. This is what you get when you do the experiment. And it's usually less than the theoretical yield unless you have contamination, and then it might be more. The percent yield is when we would compare the experimental yield to the theoretical yield. So we just compare using a ratio, using math, do your experimental yield divided by your theoretical yield. And then, of course, convert that decimal to a percent by multiplying it by 100, or just move the decimal twice, whatever works for you. Now, in redneck terms, here's what we say. You take what you got, and you divide it by what you should have got. And of course, you have to turn that decimal to a percent also. So let's work through these different types of expressing the yield in our reaction. Aluminum burns in bromine, producing aluminum bromide. So in a laboratory, if 6 grams of aluminum reacts with excess bromine, 50.3 grams of aluminum bromide are produced. We are supposed to find out what are the 3 types of yield. So to start this, I need a balanced equation. Aluminum is just Al, the solid form of aluminum, and we're going to burn it in bromine. Remember Brinkelhoff elements? Bromine is diatomic, so it comes in pairs. And we're going to make aluminum bromide. Make sure when you write this chemical formula, you crisscross your charges to get it to work out correctly. Now let's balance the equation. And there's our reaction. So first I had to translate the words into the equation. Now let's turn the numbers into something meaningful. So if I start with 6 grams of aluminum, then how much aluminum bromide should we produce? Let's find out. So 6 grams of aluminum represents how many moles? Let's find out. 27 grams per mole is what the periodic table says for aluminum. And then my balanced equation says I need 2 moles of aluminum for every 2 moles of aluminum bromide. And now I need the mass of aluminum bromide, 1 mole. Don't forget, there's 3 bromines here. So add 3 bromines together with 1 aluminum, 267 grams per mole of aluminum bromide. So now, calculator time. 6 times 2 times 267 divided by 27 times 2. Don't forget to put parentheses around your denominator to hold it all together. All right, 59.33 grams should have been produced. So what does this one represent? Which type of yield do we call this? This is what we should have made. So the theoretical yield is what we call the amount of stuff that we should have produced. That would be 59.33 grams is what we should have made in the lab. But in the lab, what was actually produced, the experimental yield, also known as actual yield, was 50.3 grams. And therefore, our percent yield is when we compare those two numbers to one another using a fraction. So 50.3 divided by 59.3, and then change that decimal to a percent, like 85%, or we could call it 84.8%, so we can keep our 3 sig figs. There's our percent yield. Years of experience have proven that the percent yield for the following reaction is 74.3%. So if you're getting a 74.3, you're hitting the industry standard, and you're doing really well. So now let's answer the question. If 10 grams of mercury and 9 grams of bromine are reacted, then how much mercury bromide will be produced? Well, first we have to see what's going to run out first. Is it the mercury or is it the bromine that runs out first? So we have 2 starting amounts. That means we're going to do 2 T tables. And mercury is a really heavy molecule or a heavy atom that weighs 200.6 grams for every mole of mercury. And then my balanced equation, I didn't even write it yet. So where's a good place? Let's squeeze that in up top here. So mercury plus molecular bromine, elemental form, makes mercury bromide, HgBr2. Well, that makes my balancing easy. Look, that's not too bad. So for every 1 mole of mercury, I form 1 mole of mercury bromide. Notice that a limiting reagent is always going to be something on the reactant side. It's never anything on the product side. Just FYI. And I need to get to grams, right? Yeah, let's go ahead and go to grams. Okay, so then 1 mole of mercury bromide weighs how much? Add 200.6 to, let's see, bromine is 80, so 160 plus 200, that's a big molecule too. I didn't go to grams. I guess we don't have to. Let's not go to grams. Nobody's got time for extra work. Let's just figure out moles and work it through. Calculator time. 10 divided by 200.6, and then my mole ratio is 1. So 0.049, blah, blah, blah. 0.4985 moles. Now let's compare the bromine. If I have 9 grams of bromine, that means 160 grams of bromine make up 1 mole, because there's 2 atoms of bromine in every molecule. And then my mole ratio is 1 to 1. So that's not too hard. 1 mole of bromine makes 1 mole of mercury 2 bromide. And then we'll run the calculator through this one. So 9 grams divided by 160 grams per mole times 1 divided by 1. Don't need a calculator to multiply by 1. Don't do that step on your calculator. You'll feel like a fool. Okay, which one's the smallest? Can you tell? Oh, I skipped a number here. There should be a 9 right there. And that's my smaller of the 2 numbers. But now let's apply the percent yield. Industry standard says 74.3% of that will be made. So what is 74.3% of 0.04985 moles? Multiply your percent times your moles. And I got 0.04179 moles of mercury bromide. So now I want to turn that into grams. Now I'm ready for that step. Okay, part B says if the reaction did go to 74.3% completion, how much excess reagent would be left? Well, now since I already used my limiting reagent to get my product, I'm going to use my product to work my way to how much excess reagent was reacted. So I'm going to turn moles of mercury 2 bromide into grams of bromine gas or liquid, whatever it is. And then we'll be able to see how much is left. So I have moles of mercury bromide. Let's turn it into moles of mercury. This is a 1-to-1 mole ratio. No big deal. And so let's do the calculator. 0.4179 moles times 160 grams per mole. I get 6.686 blah 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 blah. Well, that 87 grams of bromine. And what did I start with? Because it says how much is left. So if I start with 9 grams and I use up 6.687 grams, then I'm left with 3 sig figs, let's see, 2.31 grams of bromine remaining. Okay, here's our last one. Commercial brass is an alloy of copper and zinc, and it reacts with hydrochloric acid by the following reaction, where zinc reacts with the hydrochloric acid, but the copper does not react. So if we have 0.5065 grams of brass reacting with excess hydrochloric acid, then eventually we can isolate the zinc chloride so that all the zinc is used up. So if we can go from grams of zinc chloride to moles and then grams of zinc, then we'll know how many of this is zinc and the rest would have to be the copper. So let's work this one out. I have 0.0985 grams of zinc chloride. And the molar mass of zinc, let's see, I have chlorine is 35.5. How much is zinc? 60-ish? 65? Okay, so add those up. I got 136.28 grams, pardon me. All right, then my mole ratio is, let's see, 1 mole of zinc chloride comes from 1 mole of zinc. Whoops, not enough bumps on the M. We're almost there. Let's go to grams of zinc now. 1 mole of zinc weighs 65.38 grams. So get your calculator out. So we have 0.0985 times 65.38. Then divide by Oh, I didn't need parentheses. 136.28 grams per mole of zinc chloride. And that's done. 0.04. Okay, so not a whole lot of zinc in that bad boy, huh? 0.047255 grams comes from zinc. And we had 0.5065 grams of brass, which is zinc and copper together. So that's going to be 0.047255 grams of zinc plus some unknown grams of copper. So we're going to subtract these to get our grams of copper. And I got in my calculator 0.4592 grams of copper. Most of that brass was from copper, wasn't it? So let's find the percent composition. So the percent of zinc in the brass is 0.0473 over 0.5065, and then multiply by 100 to get your percent. I got 9.3% is zinc, and the rest is going to be copper. So 100 minus 9.3 gives us 90.7% copper in your brass. That's a very high copper content for most brass, but that's the numbers we got. So that's how we use stoichiometry to solve AP chemistry problems. You're going to practice this so much that stoichiometry is going to be like breathing. You won't even have to think about it. You just do it. See you guys later.